All right, so let's get started. It's 3 o'clock, I guess. Jack off. There's no air conditioning in this building today. All right, so let's put our cameras on if we can. All right, so I know we're supposed to move forward and start talking about the next chapter, stress and strain transformation, but I did want to do more combined loading problems because they are so critical that you're able to kind of do these. Okay, so I wanted to do a couple of more of them, as well as have you guys work in groups on closing some of them out as well. And I will promise to have a little more time to go through and see how it's going in the groups as well today. Okay. So, are there any questions before we get started on the combined loading material? Difficulties people are having? So hopefully, what you can see is the big issue is trying to figure out, I think there's really two difficulties that come from doing these things. One is to look at the loading and then try to take that and like determine, okay, there's going to be torsion, there's going to be bending around this axis. That's the first issue. And then I think the second issue is, in fact, trying to visualize how the different types of bending mechanisms, the different types of mechanics and materials mechanisms, torsion, bending, transverse shear, how they show up on the little cube of material, okay? And so I posted some problems with PowerPoints that kind of go through all that stuff. And I think you should look through those. There's videos that support that stuff as well, but they get a little bit tiring. So I think the best thing is just to start to go through some more problems and I'll talk through it. Okay. All right. So if there's nothing else, the first one I wanted to do is problem 858, which is again, a pretty typical problem here. There it is. So I think there's like 3 variants of this in the textbook, and almost every textbook has some variant of this sort of street sign problem, right? So here is what you might see driving down I-10. It's some sort of sign cantilevered off of a post with a uniform wind loading. So they give it as a pressure, 1.5 kilopascal pressure acting on that surface. And they want you to figure out the states of stress, the stress components, acting at points C and D on this cross section. Of course, you could also do them at A and B as well. And it's really not a bad exercise to go through that stuff, okay? So the first thing you really want to talk about doing, right, is, again, remember, step 1 is to, from the loading, determine what types of mechanics and materials stresses are on the cross section. So MOM is mechanics and materials. Okay, so they tell you to figure it out on this cross section at this point. So you have to be able to look at this and say, okay, this is going to produce torsion around the z-axis, a bending moment around the y-axis, a shear in the x direction, whatever it is, right? And that's the first thing that you need to be able to figure out. The second part is then to take those loadings and then determine the stresses. Oops, I should say from step 1, right? And then the last part is to visualize or realize that on the little differential element, realize the stress components All right, those are the 3 steps. And again, as previously, this has been our major focus in this class, but this is going to kind of require that you're a little more comfortable with that stuff. And then clearly, this is a major issue. When you knew we were doing stuff from chapter 6 on bending, clearly you knew these were bending problems and you had to use MCNI. But in real life as an engineer, you're not going to be at a design review and they say, okay, what's the bending stress? You have to look at the structure, see the loading and say, okay, there's going to be torsion here, there's transverse shear, there's axial, whatever, right? And this is also a needed thing because in fact, you have to look at how the loadings contribute either to make the stresses higher or less, okay? All right, ultimately, when you go into design, the next class, right? All right, you're going to need to know what those stress components exactly are, what the normal stress in the X direction, the Z direction is, the shear stress in the ZY plane, the shear stress in the XY plane, so that you can put those into the appropriate failure models, like von Mises or whatever, and see if the component fails, okay? Which we kind of don't do in this class, but there's actually a chapter at the very end of the book that does that, but we don't usually cover that, okay? All right, so let's do that, okay? So step 1, let's look at the loading we got here, and let's figure out, because of that wind loading on the side, what does that do at the cross section 3 meters below the sign, okay? So the first thing you can do, right, obviously, is you got a distributed load here. The effect that it's a distributed load doesn't really affect what's going on so much at the cross section. So we can consider this easily to be a point load acting right in there. And that point load is going to be the 1.5 kilopascals over the area. So that is a 3 kilonewton force acting right at the center of that sign, right? So that's 1 meter here, and then a half of a meter up, right? All right. So step 1, what are the stresses, or what are the types of loadings on that surface? Okay, so I'm going to draw that surface a little bit bigger, if I can zoom out. So imagine this is that surface. I'm going to make it big so that I always try to make it big so I don't write all over myself, but I end up always doing that anyway. Here is the x-axis. Here is the y-axis. And here is the z-axis, okay? All right, so you can go through this like chapter by chapter, all right? All right, and please, I want people to chime in on this, all right? So will this loading put any axial, either tension or compression loading on that cross section? P over A types of stresses. Yes or no?
I don't think so. So no.
Yes, that would be no. Anybody else see it differently? All right. So then moving forward, torsion, bending, transverse shear, what else? What do we see from that 3 kilonewton force? What type of loads are going to happen on this cross section? Like which chapters come into play here?
I would say torsion, bending, and transverse shear.
That's right. That's right. So the 3 kilonewton force, right, acts on this 1 meter torque arm and is going to produce a torque around the z-axis. So what is that going to do on this face? It's going to produce a torque that goes like this on that surface as I've drawn it, right? I know technically I probably should draw the opposite surface on here, but this is, as it would directly act on that surface. And that's the direction it would act. And this is going to have a value of 3 kilonewton meters, right? Because its moment arm is 1 meter. All right. We got two choices for bending around the y-axis, bending around the x-axis. Do we have either of those or both of those or neither of those?
Only bending across the Y.
Yeah, you got a bending about the y-axis, right? It's going to tend to make this thing topple over in that direction. So what's the moment arm that's going to act on that 3 kilonewton force is going to act on?
3.5 meters.
Right. It's the 3.5 meter moment arm, right? And that's going to act around the y-axis. So you're going to have a bending moment that's going to want to go like, I'll use a different color, right? Like that, right? Around the y-axis. This is a moment around the y-axis, and its value is going to be the 3 kilonewtons times 3.5 moment arm. And so what is that? 10.5. All right. Bending moment around the x-axis. All right. What if we wanted to consider the weight of the sign? What would that do?
Yeah, then that would make it
Would it do-
bending across the
Right. So imagine we wanted to consider the weight of the sign, which is not in the problem. I agree with that, but let's just do a thought experiment. So there would be a weight going right through the same, right? Imagine it's with 100 kilograms. So that would be 100 kilograms would be roughly 1,000 newtons of force acting down, right? Assuming like gravity is 10 meters per second squared. Okay, a downforce, that what type of stresses, what types of loading would that add on to this cross section?
A normal and a bending about the x-axis.
You get a bending about the x-axis. The moment arm would be this. Is that what? It's 1 meter, right? The 1 meter, right? So it would be a 1,000 Newton meter bending moment around the x-axis. What else would it do? It would add another component as well.
A normal stress.
What's that?
A normal stress.
Right, a compressive P on A stress. Does that make sense? Right, an axial stress, right? Because that would put a uniform pressure over area on that. Again, you could think about relocating that to the center line, and then that would produce the moment as well as that force, right? But the problem didn't ask that, so let's not carry forward on that. But if they did, that's what you would need, right? And
Professor,
yes,
just one question on
Sure.
that. Would it have transverse shear as well, or no?
yes. Yeah, let me just label the points, then we'll get to that.
Okay.
So what is this? AC, this is D, and this is, oh, sorry, this is D, and this is B, right? Right. Okay, so yeah, what else is going on here, right? Whenever you have bending, you're almost always going to have a transverse shear, unless there's a pure bending moment being applied, which doesn't happen that often, but usually the bending moment happens because of some load, and so that will also tend to produce a shear on here, right? So which way is the shear going to act?
On the x-axis?
Yeah, actually, going into the negative axis, but right, it's in the x direction, so it would actually go this way, and the value would be the 3 kilonewtons, right? All right, so what are we going to have? This stress here, right? this is going to produce a shear stress TC on J. Okay. This transverse shear stress is also going to produce a shear stress, but it's evaluated as VQ on IT. Every time I do a fraction, I get a triangle. Okay. And then lastly, the bending moment here, right? This is going to produce a normal stress of the bending type, MC on I. All right, so step 2, let's calculate those stresses, okay? And specifically, you know, what do they want? They want us to do it at C and D. So at this point and this point, okay? So let's go through and we'll just do that for both points while we're at it, all right? So, well, first let's compute the geometric quantities, right? So what is the diameter here? I don't even know. 100 millimeter diameter. Okay, so it's 100 millimeter diameter. So let's get the area, right? So the area of the cross section, 0.1. So the area is going to be 7.85 to the minus third meters squared. J is going to be 9.81, well, really 9.82 to the minus 6 meters to the fourth, and I is going to be half of that, which is 4.91 to the minus 6 meters to the fourth as well. And we'll have to do Q, but let's kind of hold off on Q until we know exactly, like, I want to talk a little more detail about the cross section that we use for calculating Q, okay? All right, so if that's the case, let's first do the TC on J, right? So in this case, the tau for TC on J, the torque is 3 kilonewton meters. The C is the radius, right, which is 0.05 meters, and that's going to be over J, which is the 9.82 to the minus 6 meters to the fourth. And that gives me a shear stress of all right, I get 15 KS, 15 kPa, right? No, I got K, so that's actually 15 megapascals. Okay, that's the shear stress, the value for the shear stress we get. And that would be the same at C, B, A, or D, correct? So this is what you'd get, different components, but this is what we would get at A, B, C, and D, right? Because they're all on the outer diameter there. They all have the same value of C, all right? Okay, let's look at the bending stress. All right, so now when we talk about the bending stress at D, here is the neutral axis, right, for that bending shown, the was it 10.5 kilonewton meter. So at point D, the value of C is 0. It's at the neutral axis. So there is no bending stress there at all, right? So this is only going to be at D. So this is at D. At point D, or actually also at, I'm sorry, at point C or point A, right? It's going to go to 0 at B or D. And in this case, the M is 10.5 kilonewton meters, right? The C is still the same, the 0.05 meters. And then the I is going to be the 4.91 to the -6th. And that gives me a value of that gives me 107 megapascals. Okay, and that's going to be at points A and C, and lowercase c equals 0 at B and D. So therefore, the stress is 0 there, right? At those 2 points, okay? If you had a bending moment around the x-axis, it would be the opposite. Points A and C are on the neutral axis, so the stresses there would be 0. And then you would have the maximum bending stresses at points B and D, all right? Now, if you look at this, we know it's a normal stress, and well, I'll go back to this in step 3, but it's going to be tensile at A and compressive at C, but we'll talk about that in a second. All right, and then the last one is the transverse shear stress due to the bending, the VQ on IT stress, okay? And so let's do that one. All right, so when we first do that, right, okay, here's the transverse shear. Where will the transverse shear stress be maximum? Which points? And where will it vanish?
It would be maximum at A and C.
No, actually at A and C it vanishes. It's maximum at B and D. It's the opposite of bending, actually.
So it will be maximum at the neutral axis.
That's correct. So right. So let's draw it. Like here is the circle, right? And here is A, B, C, and D. A, B, C, and D, right? So this is B. This is C, and this is D. And we have the 3 kilonewton force acting up this way, right? All right. So if we talk about point C, the area that we would consider for computing Q is the area above, we want to get the shear at this plane. There is no area here. So up here, right, Q goes to 0, right? And likewise at point A as well, Q goes to 0. Now, if we talk about points B and D, we want to get the shear acting on that plane. And so there, the area we're going to consider is this area here to calculate Q, right? You need the area above the plane where you want to calculate the shear. So this is the Q we would use for points B and D. They would be maximum, right? And so it's a little hard to remember, but the centroid of a half circle, this distance here, is going to be pi over, I always forget what it is, pi over 8 diameter. Wait, pi, what is it again? 2, right, okay, that's what it is. Sorry, I'm thinking that it was over Q. It's 2 D over 3 pi. Okay, right? So the shear stress, the transverse shear stress goes to 0 at points C and A and is max at points B and D. All right, so let's figure out Q for these points. Okay, so remember Q is going to be the area of the shaded area, A bar, times the distance to the centroid, okay? All right. Okay, so in this particular case, the area is, half the total area of the circle. So it's pi times the diameter squared over 8, because it's half the circle area. And then y bar is going to be 2d over 3 pi, 2d over 3 pi. The pi's cancel out. This 2 will make this one be a 4, and that leaves us with d cubed over 12, right? 3 times 4 is 12, yeah, right? Or in this particular case, that gives me a value of 83.3 to the minus 6 meters cubed. Okay, that's the value of Q, all right? So remember Q, it depends, the Q changes depending upon what plane you want to compute the shear. And that's why advantage is at A and C. And is max at B and D. All right, so we can calculate that, right? So we know that the transverse shear stress there is going to be V, which is the 3 kilonewtons, times Q, which we just calculated as 83.3 to the minus 6 meters cubed, over I. So that's I for the whole cross section, which is the same I we used in the bending, 4.91 to the minus 6 meters to the 4th. And then T, right, times T. And T is going to be this thickness here, because that's the plane of interest. This is T. So it's the diameter, right? 0.1 meters. And that's going to give me a shear stress. These are usually very low. Yeah, it's pretty low. So here we get basically a half of a megapascal, right? 509 kilopascals. That's kPa. So that's really small. And this is always very typical. The bending and the torsional stresses are the highest. Almost always bending stress is the worst one. That always causes the most issues. And then unless you have a really stubby section, beam type of thing, which is clearly what's not going on here. That post is a very long, slender beam. So the transverse shear stresses are not surprising to go to 0, okay? All right. Sometimes there's a little bit of confusion. People say, well, what about the shear stress? That was the shear stress over the area, right? Remember back in the way beginning, I guess chapter 1 or 2, we talked about shear stress being the shear force over the area. So do we consider that here? How does that type of shear stress relate into what's going on here? Remember, like when we did shear in a pin.
That was the average stress?
Yeah, exactly. Very good. Yeah. It is the same. It's trying to get to the same type of stress. They're both the shear stress due to that shear force V. But this one is more of an approximation. This one is a bit of a more accurate description of how that shear stress evolves over the cross section. So really, like when you have those shear pins that we talked about early on, or a bolt, honestly, it's still this type of shear stress. This is a little more accurate description of it, right? Right? It's actually not going to be uniform over the cross section. It vanishes up at the tops and the bottoms and is max at the middle. Okay. All right. So that's the second step. That's all step 2. We've got step 2 down, right? This is all step 2. This is all up here. This is all step 1. All right. So let's go back. And now we got to do step 3. Now we have to take those values and we have to draw little differential cubes of material at point C as well as point D and see how they contribute there, okay? So let me zoom back in a little bit. So what was it, about 100% up there? And let's just redraw the cross section. All right, so there's the cross section. We have the X and the Y axes going this way, right? So this is point B. This was point A. This was point C. And here is point D. And so we're going to draw the little differential element down here on this sort of region, okay? Oops, come on. What does this? Go away. So we're talking about this bottom region here, right? So X, Y, Z. So this was the X-axis. No, wait, is it the Y-axis? I forget which. It should be the X-axis, right? Yeah, X, Y, and Z. Because these are. This is the X-axis going this way. This is the Y-axis going this way. And then that means the up axis here is going to be Z. All right, so let's first look at a little differential cube at point C. Let's do that one first. So I'm going to kind of blow that up, but keep it sort of oriented in the same way. So that top surface that I just drew there, that's the surface that's exposed by that cut, okay? All right, so let's go through and let's figure out where these stress components act. Let's go one at a time. All right, so first, let's do the torsional shear stress, this red one, the 15.3 megapascals. How does that shear stress act on point C? Like if you look down at this little cube, how is it going to act, right? Remember, this is the torsional torque there. The moment was it 15 point? I can't remember. It was 15, 10 point. Yeah, it was 10 point. No, it was 3 kilonewton meters, right? This is the 3 kilonewton meter. All right. Well, how does that show up on this little cube of material? The 15.3 megapascal stress. So we know it's a shear stress, correct? What plane does that shear stress act on?
On the XY, I think.
All right. that's the face it's acting on, but that's not the shear component. What, just think about the traction on this top cut face. Oops. I hate this thing. Ugh. Go away. Just on this face, how would that traction act? Which way is it going to go? X, Y, probably not the Z, because that would be a normal stress, right? It's either going to be the positive X, the negative X, or the positive Y, or the negative Y. Which way is it going to go?
Negative one.
That's right. It's going to act in the negative Y. Always think about it. I mean, I think it's, you know, like if here's the surface that's cut, right? That torque wants to shear around if you're looking down on it in a counterclockwise manner. So that means its traction is going to act at point C in the minus Y direction. At point B, it's going to act in the minus X direction. At point A, it's going to act in the positive Y, and at D, it's going to act in the positive X, right? So it's going to act this way at point C, this way on that top surface at point B, this way here, and then this way here. Does that make sense? Right? So it's going to act on this face here. This is C. All right. We should just, while we're at it, we probably should just draw the cube for point D as well. So I'm going to put that down. Right? So what component is that?
The torsion.
I know, but what type of stress is it? It's a shear stress, correct? So shear stress acts on a plane. Is it X, Y, Y, Z, Z, X? What is it going to be?
XY.
Nope.
YC.
That's right. In this case, it's acting in the YZ plane, right? Because its couple friends are going to be right. Obviously, on the bottom face, it's going to act in that direction, right? And then it's going to act that way as well as up that way, right? So this is a tau YZ, and that's going to have at least the 15.3 megapascals. All right, here is the $10,000 question. Is that technically a positive XY shear stress or a negative XY shear stress? Who remembers the sign, how we determine what's a positive sign convention for shear? You can look at this face, right? That face that I shaded in blue, is that an X face, a Z face, or a Y face? Which direction is the normal?
In the Z.
It's in the positive Z. So the positive, on the positive Z face, which direction should the positive Y, Z, or I should technically say ZY stress act? Only two answers. Should it go in the positive Y direction or the negative Y direction? It's clearly not going to go in the X direction. Otherwise, it would be a ZX stress. positive face, the traction acts in a positive direction, right? You guys got to review this stuff, okay? That's what I'm talking about. This is the stuff that, you know, you didn't have to absolutely know this when we did torsion, because everything was just report TC on J, even though you had no idea how it really visualized or manifested itself on the component. That's kind of no longer acceptable. So this is actually a negative tau YZ stress. This is actually negative. This is actually a negative tau YZ because it's pointing in the negative Y direction on the positive Z face. All right. All right. What is it doing on point D? What type of shear stress are we seeing at point D due to the torsion?
There's a shear stress in the negative X direction.
That's right. So it's going to act in this direction, correct? And so
Yes.
it's going to have its friend acting in that direction and then the couple pair going like that, correct? So what type of shear stress is that?
This is negative.
It is a negative. What's the component though? X, Y, Y, Z, Z, Y.
The CX plane.
That's right. It acts in the ZX plane. And it actually is, since this is a positive Z face, and since the traction's acting in the negative X direction, it's actually a negative value. That's right. So it's technically a negative value, but it's drawn that way. So that would be tau XZ or ZX. Technically on that face, it's ZX and its value there, you know, I guess I should put a negative here, right? But it's the 15.3.
Professor, can you explain that concept a little bit more? Because I'm not getting it.
Like, how do you know? Okay, right. Yeah, shear stress is the trickier one, right? So the first thing, there's two things that you gotta be able to do, right? The first one is, what's the plane it acts on? That's like the first thing you have to answer. Is it an XY, YZ, or a ZX? Okay, so the way I do that for torsion is I see here, you know how I shaded the top surface that I've exposed by cutting it. Does that make sense? That's what I've shaded in blue, right? That's what's supposed to be going on here, right? That's the exposed surface. So for me, it's easier to visualize the traction due to that type of loading on that cut surface. So I can draw this vector quite easily, or this traction vector here quite easily. Likewise, at point B, it would act in this direction, and at point A, it would act in that direction. Does that make sense? I find that easy to do, okay?
Could you almost say that the X direction would be the direction that the shear is acting, and then Z would be the rotation of the torque?
That would be, okay, so let's be really careful about, what you're saying is true, but don't say shear, the shear traction on that face. So on those blue faces I showed there, for example, on D, right, at D, on that shaded top surface, the shear traction is, yes, in the negative X direction. Does that make sense?
Yes, sir.
But if we thought of the face below it, right, this face that's kind of hidden under here, that's a negative Z face. The traction would actually go in the positive X direction. on this face here, which would be a positive X face, the traction is in the negative Z direction. And on its other friend, it's in the positive Z direction. Okay, so now we know which plane it is. So clearly here, it is going to be acting in the XZ plane. Technically, the first index is the normal and the second index is the direction. So that's how I say this traction up here is really technically as it's drawn there, is a negative tau ZX because it acts on the Z plane in the X direction. This one is technically a negative tau XZ. X face acting in the Z direction. But okay, but you know these shear tractions have to act as couples. So that allows us to draw the little couple friends, right? So like on this one at point A, you know it's going to have its little couple friends going that way and this one going that way, right? Likewise here, you know it's going to go like that. Does that make sense? So when you draw the couple friends, right? What do you want to call them? I mean, they're not really friends, I guess. I don't know. Maybe they are. That clearly you can see the plane it acts. Does that make sense? So that's when I always say shear acts in a plane. So at points A and C, they are ZY shear stresses. At points B and D, they are going to be ZX. All right. Now, how do you know the direction? Is it a positive or is it a negative? That's the sort of the next level discussion. All right. So here's how I check. Okay, this, like, let's look at this one right here, right? All right. This one acting on that face. That is a face whose normal direction is in the positive Z direction. So that means the positive traction, the positive direction for the ZX traction has to be in the positive X direction. But what I drew here is actually in the negative X direction. So it's a negative component. Does that make sense?
So it just follows the normal X, Y, and Z coordinates. So let's say, for example, the C component goes down and the X component goes to the right. So that's why they're negative.
No. So you could even do this bottom surface. I don't want to draw on it too much because then when I do the other ones, it's going to have to be a real mess. But like if you look at this, this will always work out. Let's look at this bottom surface here, okay? That one is a negative Z surface. Its normal direction's in the negative Z direction, correct? So which direction would a positive ZX shear stress component, traction component act in? The positive X or the negative X direction?
The negative X.
Yeah, it's the negative X direction. Everything flips. It's a negative face. So the positive ZX shear stress traction on a negative Z face has to act in the negative X direction. Well, here on this face, it actually acts in the positive X direction. So it is a negative shear stress, okay? And of course, it has to be a negative, and you can do that on all four of those faces. They're always going to come out to be negative. They have to. It's the same shear stress. It couldn't be positive on one face and negative on the other. It's either a positive shear stress or a negative shear stress, right? The tractions might point in different directions because they're on different faces. But the shear stress itself, in this particular case, it's negative. All right, let's talk about, so here's that question. So, okay, point B. This is point B, right? This is clearly a tau XZ Z. It acts in the XZ plane. The way I've drawn that there, is that a positive or a negative XZ shear stress?
Positive is, yeah, is the opposite than point D, no?
Okay, forget about what's at D. Don't say opposite. Don't try to guess. Don't try to, okay. Forget everything else. You should be able to determine this just by looking at it, right? Look at the axes. What's the positive direction? Is that a positive XZ shear stress as I've drawn at point B, or a negative?
That's a positive.
Yes. Why?
Because both the Z and the X point in the positive direction.
That's correct. The traction on the positive Z face is acting in the positive X direction. So that means it's a positive shear stress. If you were to look at the back face here, right, the one that you can't see, that is a negative X face, right? And the traction component is in the negative Z direction. So the negative Z direction on a negative face is the positive sense. So it's positive there. It's positive on all four faces because of what I said before. You know, it's if it's positive on one face, it's positive on all the faces, right? All right. What about a point A? Positive or negative? And what type of, what's the component of shear stress? Okay, first, what's the component of shear stress? What plane does it act in?
YZ,
YZ, positive or negative?
positive.
That's right, because it's acting, if you look at this is the positive Z face, right? So a positive ZY traction on the positive Z face has to act in the positive Y direction. And it is, so it is positive. They all have the same values, the 15.3 megapascals, right? But they have different components and different senses depending upon where you're at, A, B, or C, or D, okay? All right. So, okay, that's shear stress. And I think shear stresses are always going to be the harder ones to visualize, right? And, you know, torsion has that pinwheel thing. If you do a couple of them, it gets a little bit easier. All right. Any questions on that one before we go into the bending? All right, let's do the bending. Okay. So now we got bending stress. There it is. We computed the value, which is pretty plug and chug. You don't have to think too much on that. It's 107 megapascals, right? All right. So that bending moment is going like this, right? There it is. And that, what was it? 10, that was the 10.5. I always forget. That's, oh no, it's 10. All right. So there it is. Let's go through all the points. What type of stress is that bending stress, right? This produces the 107 megapascals, right? The MC on I. What type of stress does that produce? Let's start off at point A, down here. How does that bending stress show up on the differential element at point A?
Like a tensile stress?
Tensile stress, right? Is it positive or negative? Tension or compression?
Tension.
Tension, right. Okay, so what type of stress component should that be? It's going to go this way, right? We know it's going to go this way. And on the negative face here, it's going to go that way, right? And that's the, from the bending, right? So I'm trying to use the colors to denote what they come from, right? So I don't have to make it too messy. What component is that? Sigma X, sigma Y, or sigma Z? It's a normal stress, right? It's a normal stress. What direction?
Sigma Z.
That is a sigma Z stress. That is a positive sigma Z stress. All right, what's going on at point B? What type of stress does that put at point B?
No.
None, yeah. I mean, I guess technically it is a sigma z, it's a normal stress in the z direction, but its value is 0. So it doesn't do anything there. I don't even draw it. Okay, what about at point C? Now we go up to point C. What's it going to do at point C?
A compressive normal stress.
It is right. It's a negative normal stress in the z direction, right? It's going to go like that. It's a compressive stress, right? Exactly. And its value is 107. And again, likewise, at point D, it does nothing, right? Because it's at the neutral axis. So yeah, bending stress is a little bit easier, but again, it's important that you can visualize where it goes to 0 and also on which side it's in compression and on which side it's in tension, right? Because if they're, like, again, if we considered the weight, remember we talked about the weight of the sign, and that would have put a P on A compressive stress over that entire face, correct? It would have made the stress greater at point C because they would have both been negative Z stresses and they would have added together. Whereas it would be of a different sign, it would be compressive and subtract from that positive bending stress at point A. Does that make sense? I mean, we can figure it out real quick. What did I say just for the goof? I said it was 1,000 pounds, 1,000 newtons, right? So the P on A stress, if you just wanted to consider it, there's the area, the 7.5. Sorry if I'm being too, like, I was wondering what I should get into all this detail about. So that is a 100. If you consider the P on A stress, right? You should probably have a different color. No, I use green for some colors, the purple. The P on A stress is 1,000 newtons over the 7.85. That gives me a normal stress of 127 kilopascals, right? So that would be a compressive stress everywhere, right? So in this case, we would subtract off another 127 kilopascals, and then you would also have that in compression on all those other faces, right? Does that make sense? So you would get that, the maximum compressive Z stress would be right there at point C, okay? But again, it's still the bending stress is really dominating, okay? But it didn't ask that. All right, so now finally, last one, right? Last one, transverse shear, right? So we already talked about that the transverse shear vanishes at A and C. It doesn't do anything at A and C, and its max at points B and D. So let's look at D, all right? All right, what on this cut blue face, the top face at point D, which direction does that 3 kilonewton traction act? Which is here, right? Like this one's easier, right? It's going to act in the same direction as the shear, correct? Due to the torsion. It's going to act in this direction. Does everyone see that? So again, it's a negative ZX, and that has the value of the 509. Correct? Now, what about at point B? It acts in the other direction, right? Like they act destructively. And it doesn't do anything at points A and C. Does that make sense? All right, so we're not quite there yet. I mean, we basically are, but we should get the proper answer, okay? So if we were to do, here's how the answer should be reported. At point C, this is what you should draw. Here's the little chunk of material. I don't know why I decided to do it that way. All right, and I would draw the actual components on it. So we have a compressive stress like this of 107 megapascals, right? And then the shear stress is going to be this and this, right? And that is 15.3 megapascals. That's the way you really should draw it, in my opinion, okay? That clearly explains the state of stress at point C. This is at point C, right? If you want to be technical about this, you could also say that the normal stress in the Z direction is minus 107 megapascals. And the shear stress in the YZ shear stress equals the ZY equals the YZ, and that equals minus 15.3 megapascals, right? Because as we talked about, that is actually acting in the negative direction, okay? Now, if we were to do the same thing for point D, there's the, just terrible drawing. Let's try to draw a little better. Now you can also see why I'm a little bit of a jerk about trying to draw things neatly on exams, because you know, if you don't do this neatly, it's just impossible to figure out what's going on, right? All right, so there's point D. All right, so what do we have at point D? Well, all we have is the shear stress acting in this direction and this direction. Right? You can draw the back faces dashed if you want. But honestly, if you just draw those two components, that's enough to show it. And the value here is going to be the 15.3 megapascals plus the 509. So it's going to be 15.8 megapascals, okay? And so here, the only non-zero stress component is going to be tau xz, which equals tau zx, and that equals a negative 15.8 megapascals. All other components are zero, right? Right? And likewise up here, all other components are zero. Sigma x equals sigma y. Okay? Either way is fine. You know, you should be able to understand how to get the signs, you know, the directions correct. You should also be able to look at the labeled X, Y, and Z axis and determine whether they're positive or negative stress values, okay? This way or this way, they both mean the same thing, okay? All right. Any questions on that one before we let you guys try a different one? I probably could re-sign it again. All right. Is anybody still there? Are you guys all
Yes, sir, we're here.
okay?
Yeah, we're here.
never know. Of course, those who aren't here, can you please state so? It's like a bad joke, right? All right, this one's a little bit easier, I think, right? But let's have you guys do this in groups. I know you can't see this yet. Hold on a second. Let me just copy and paste it in. Well, actually, let me just do both. Let's do both. Yeah, I know. This is another one that's basically the same difference. All right, so this is the same problem, two different pictures, okay? Or, well, same picture, two different problems. It's actually a little bit easier. All right, 859 and 860. It's the same picture right here. All right. So you have this 900-pound force, and they want you to figure out. So here you got points A and B. So you have to be. It's a little tricky to see exactly what's going on here, right? But if you were to cut this section, A and B are both on the, on the face that's visible to us. But you can see here, they're not in the middle, they're on the side, right? So technically, like if you were to draw, like if we were to do like an engineering drawing, so it's perfectly clear, like this is A, the rest is G and D. So if you drew section D, right? It would look like this, except it would be square. Looking down the end, this would be point A, and this would be point B, right? And that's the cross section, right? So on the outside, it's facing us. All right, you got the 900-pound load here. That's going to obviously put normal, like a P on A stress, but it also will put a bending stress and then obviously a transverse shear on this, okay? So figure out the states of stress at point A, that's 859, and at point B, 860. So you can do it the exact same way we did it before and do both at one time, right? First, identify P on A, MC on I, VQ on IT, which TC on J. In this one, there is no TC on J, right? But you get those, and then determine the values, do the gut calculations, and then visualize how they would act at points A and B. Okay. All right, let me put you guys into groups. We don't have a lot of time.
Are we submitting this one to Gradescope?
Yes.
Okay.
On these ones that you submit to Gradescope, I do not really check. I don't really grade them like how well you did. I just grade that you submitted something. I mean, if you submit just like a picture of a dog, I'm obviously going to not give you points on that, right? But
So we could
Some basic-
just so we could upload what we have because I have a class at 4:30 and we have
I give you. Oh, okay. I'll make it. I'll make it till like 8 tonight. Okay.
okay. Thank you.
But anyway, okay. There you go.